Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our new series on equations that changed web handling forever. In this short show, I explain most everything you need to know about sizing the diameter of rollers. No worries, kiddos. I'm going to make this as painless as possible. The laws of physics guarantees that rollers will bend due to the vector combination of roller weight, web tension, and/or nip load. There are many undesirable outcomes from excessive bending. One possibility, though fortunately quite rare, is for the roller to break at the step changes in journal diameter. Another more common possibility is that the roller or drums will vibrate more if it deflects more. If the roller is a process nip, the product will be uneven. Finally, bending can cause fan-shaped wrinkle patterns, much like a bowed roller pointing upstream instead of downstream. For these reasons and many others, many in the industries have proposed standards for maximum allowable roller deflection. The most common is a Class B deflection, which, for example, would allow the roller to bend at most the thickness of a human hair under maximum loads for a 1 meter wide machine. The bending equation is quite simple, something you could do on any scientific calculator or even a slide rule. The parameters are roller diameters, the width of the roller, the width between the bearings, and the modulus of the shell. Pretty simple for engineers and other techs. The bending equation tells us several things. The first is that it is super sensitive to roller width. The upshot is, the wider the roller, the bigger the roller diameter needs to be to resist deflection. What many people don't realize, however, is that the journal length is also extremely important for simply supported rollers. That means that you can tell a good machine designer from a bad one from across the room. A good designer will shorten the journal so much that the roller edges almost touch the bearing housing. In other words, the good designer moves the frame to the bearing rather than moving the bearing to the frame. The good news is that we can resist deflection quite easily because deflection is super sensitive to roller diameter. The bending equation also tells us that some things that are not all that important. One is shell wall thickness. Another, perhaps surprisingly, is shell material. In other words, going from aluminum to steel, or steel to carbon fiber, will buy you very little compared to buying the next larger diameter of roller shell tubing or casting. The great news for all of us is that we don't have to pull out the calculator or write a spreadsheet program to size rollers. Someone, namely myself and Dr. Abbott, have done that already. The free roller bending calculator is so easy and so beautiful that Apple would be proud to have it. Yet, it is free and available to anyone with a smart device and an internet connection. I want to close with a list of other concerns that might apply to roller sizing. While deflection determines the size of most rollers, there are a half dozen other considerations for certain less common cases. Perhaps the most common of those and the easiest to understand is why you need to have larger diameters for heated and chilled rollers. That is, to get the dwell time necessary for heat transfer to do its work. I hope you have been inspired by the simplicity and the utility of the roller bending equation to size rollers. Stay tuned for next week's show when we will explain how to size wound rolls. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. Also, be sure to check out the show notes for bonus and surprise material. See you next time.